All right, welcome. So let's say we are given this problem. We're asked to find deflection at point A and we're asked to find deflection at point B and C for the beam shown below, okay, using Macaulay's method. All right, so we have this beam now. In the previous video, we did an introduction on how to employ or apply the Macaulay's method towards solving beam deflection. So we're going to apply everything we learned here, okay? So we're asked to find deflection. First of all, we weren't given reactions at these supports A and D. So the first thing to do is to obtain what? The reactions at the supports. So let's simply call here RA and let's call here simply RD. So let's now find these reactions, okay? All right, to obtain the reaction, simply, of course, you employ your equilibrium equation. Summation of all the vertical force is equal to what? 0. So we simply consider forces that point upwards as positive and forces that point downward as negative. So that's been the case. Then we simply have RA. RA is pointing upward, so it's going to be positive. Next, we have 5 kilonewtons acting downward, so it's negative, minus 5. Also, we have 7 kilonewtons acting downward, so it's negative, minus 7. And then finally on the beam, we have RD pointing upward, so it's positive, simply plus RD. So from the law, summation of force equals 0. So the whole of this is equal to 0. Okay, so RA minus 5 minus 7 simply gives us minus 12 plus RD equals 0. Now, let's send minus 12 over to this side of the equation. Negative sign causes an equal to sign becomes positive. So I'm simply left here now with RA plus RD, and that's simply equal to 12. So call this equation 1. So notice now that equation 1 is simply what? A single equation having two unknowns. So which means it is impossible to solve. All right, so the only way now is by simply what? Employing another equilibrium equation, which means take moment of force about any point on the beam. Now, if you have been following my sharpness and bending moment series, of course, I've said that to take moment on this portion of the beam, you look for what? One of the unknown and take moment about that point, because moment is simply force times distance. So pick one of the unknown, take moment at that unknown. If there's no distance between the unknown force and that point, it means the moment of that unknown force becomes 0 about that point. So you can find the moment of the other force about that point and obtain the value of that reaction. So let's simply take moment at point A because I have an unknown reaction here. I can as well take moment at point D. Since I have an unknown reaction here, I will still obtain the same result. So simply take moment at A. Okay. Take moment at A. All right. So summation of moments at point A is equal to 0. Let's consider clockwise moment to be positive, anti-clockwise to be negative. Okay, let's do that now. The moment of this force about point A, like I said, there's no distance between this force and point A, and moment is actually force times distance. Since there is no distance between this force and point A, it means the moment of this force about this point automatically becomes 0. So we simply take the moment of every other force about point A. This 5 kilonewtons force is acting downwards. Moment of this force about point A is simply the distance it takes this force to get to point A, which is 2 meters. But observe the direction now. Since it's acting downward, it will turn about this direction. So which means it actually have this turning moment or turning effect in this direction, which is what? Positive to our assumed direction. So which means this force is clockwise about point A. So the moment of this force is simply what? Positive. All right, so I'll simply have 5 multiplied by distance it takes this force to get to point A, which is what? 2 meters. Okay. Next is the moment of the 7 kilonewtons force about point A. This force is also acting downward, so which means it will turn all the way from this point to point A, going in this same what? Direction, which is what? Still clockwise. And distance it takes this force to get to point A is simply 2 plus 2, which is total of 4 meters. So the moment of this force, first of all, it is positive, and distance it takes this force to get to point A is 4 meters. So I will simply have plus 7 times 4. Okay, and finally I have the reaction at point D. This force is pointing upward, so the line of action actually goes here upward. So this force will turn about this direction. So turning effect is around what? This direction. It turns about this direction to take moment at point A. And if you notice this turning effect, it is negative toward our assumed direction, which is this force has an anti-clockwise moment about point A. So the moment of this force is negative. And since moment is force times distance it takes this force to get to point A is simply what? Total distance of the beam, which is 2 plus 2 plus 2, and that is 6 meters. So we are simply going to have minus r dy or rd multiplied by 6, and this is simply equal to 0. So here 5 times 2 gives us 10 plus 7 times 4 here gives, are you sure? 28. Yeah, 7 times 4 gives us 28. Okay, minus 6 rd equals 0. Okay, so 10 plus 28 obviously gives us 38. Okay, minus 6 rd equals 0. So let's send 6 rd minus 6 rd over here. Negative sign crosses an equal to sign becomes positive. So I'll simply have 38 equals 6 rd. So to make r the subject, we'll simply divide both sides by what? The coefficient of rd, which is 6. So that simply implies that the reaction at point D is simply equal to 38 all over 6. And rd is equal to what? So we simply have 6.3 kilonewtons. Okay, that becomes reaction at point D. So if we know the value for this reaction, we can simply substitute this into what? Equation 1 to obtain Ra. So from equation 1, okay, from 1 we had Ra plus Rd equals 12. Okay, so therefore this is now simply saying Ra plus, in place of Rd we simply put in as 6.3. That is simply 6.3 equals 12. So to make Ra a subject, simply send 6.3 over to this side of the equation. So we have that Ra becomes 6.3, sorry, becomes 12 minus 6.3. Okay. All right, so from here, R is simply equal to 5.7. All right, so we have 5.7 kilonewtons. So this becomes reaction at point A. So having found these reactions, all we need to do now is simply what? Substitute the values of these reactions into the beam and then start our what? Analysis using Macaulay's method. Okay, let's do that now and see. Okay, so we know Ra is simply 5.7. So in place of this reaction here, we simply have 5.7, okay, kilonewtons. We know Rd simply gives us 6.3. So here is simply 6.3, okay, kilonewtons. All right. So now we want to employ the Macaulay's method. And I said in the introduction video that when applying the Macaulay's method, you take a section. So you consider a section XX at a distance of X meters from point A. Now this section should cover the entire load acting on top of the beam before the ending point of the beam. So all the load that acts on top of the beam before the very ending point of the beam, take a section. That is where your section should be taken about. So if I look at this beam now, the entire load acting from A on the beam to where? Before the end, which is point D. Okay, before the end, which is point D, this is where the load ends at point C. So take a section after point C before the end of the beam. So we'll simply consider a section here. So XX, and we're simply saying let the distance from point A to the point of section be what? X meters. So distance from point A to the point of section is simply X meters. Then I said after obtaining this distance, what then is the distance of these other loads about the point of section? If I know distance from point A to the point of section, I said let that distance be what? X meters. What then is the distance of what this 5 kilonewtons force that is from point B to the point of section? So all I need to know now is simply find distance of this force about the point of section, or point B about the point of section. What then is this distance? So I said very simple. If from point A to the point of section is x, and now I am at point B, which means I no longer need what? The distance behind. And the only distance behind point B is what? 2 meters. Simply what? Take this 2 meters off from x. That gives you distance of what? This force at point B down to the point of section. So that distance is simply what? X minus 2. Simply take 2 away from what? X. Next, I need to find distance from point C to the point of what? Section. Still the same thing. Now I am at point C. Since I'm at point C, it means I no longer need what? Distance from point B and then from point A. So take these two distances away from what? Point X, or distance X. That gives me distance from point C to the point of section. And the distances behind point C includes 2 plus 2, which is 4 meters. So that means distance from point C to the point of section remains X minus 4. So that is the very first thing to do after obtaining the reaction. Next is to obtain the distances of all the forces about the point of section. Now, after obtaining this now, we can now find moment about the point of section. Point of section is simply xx. So moment about xx, which is moment xx, is simply now moment of the entire force that have been sectioned to the point of section. So first force is RA, which is 5.7 kilonewtons. Distance of this force about the point of section is still total distance from point A to the point of section, because this force is directly at point A. That's reaction at A. Okay. The distance it takes this force to get to the point of section, that is xs, is simply what? X meters. Therefore, the moment of this force about that point becomes simply 5.7 times x, so which is 5.7 x. And again, I said, when taking moment, according to Macaulay, every force pointing upward should have a positive moment, while every force pointing downward should have a negative moment. So therefore, you can see here, 5.7 here is positive. Okay, but then from point B, this force is pointing downwards. So the moment of this force is going to be what? Negative. But according to Macaulay's method, after the moment of the first force, as we move to the next force, we now introduce what is called the Macaulay's bracket. So you must always put this bracket to segregate or separate each of the forces and their moment about the section from themselves. Okay, so after the first force, 5.7x, that's the moment of this force now. We are now at point B, introduce the Macaulay's bracket. So take note, the sign goes inside the Macaulay's bracket, not outside. So instead of minus outside first, you have to take the minus inside. This force is pointing downwards. The moment of this force is going to be negative according to Macaulay. So I will simply have minus 5. Distance it takes this force to get to the point of section, we have established that to be what? Simply x minus 2. So it becomes minus 5 times x minus 2. Close. I still have another force at point C, so which means I will still introduce another Macaulay's bracket. Bring it down. This force is pointing downward, so it's going to be what? Negative. It's going to have a negative moment. So minus the value of the force, which is 7. Now, the moment of this force about the point of section is simply what? The force times the distance it takes this force to get to the point of section. And that distance is simply x minus 4. So I'll simply have minus 7 times x minus 4. This gives me what? Moment equation from Macaulay's method. It's as simple as this. So using Macaulay's method, we just generate a single equation. After generating this single equation, we can now employ our bending equation to find slope and deflection equation. All right. So from bending equation, okay, from bending equation, we have that the flexural rigidity, that's EI, please take note, the product of Young's modulus and moment of inertia is called, so take note, the product of Young's modulus and moment of inertia is called flexural rigidity. So the product EI, okay, d squared y all over the x squared is simply equal to moment about xx. So this is the bending equation. Okay, so ei times the squared y over the x squared is simply equal to the moment. So if this is the case, this is now the moment about the point of section we've obtained. So it simply means ei, the squared y over the x squared, is now in place of this moment. We simply put in what? These values. So we're going to have ei d squared y all over the x squared is now equal to, so in place of mxx, we'll simply put in the moment at the point of section, which is 5.7x. So we have 5.7x Macaulay's bracket minus 5 into x minus 2 Macaulay's bracket minus 7 into x minus 4. Okay, so we end it there. So that represents the moment. Okay, now to obtain the slope equation, I told you slope simply means dy dx. So obtain the slope equation, we simply what? Integrate. So integrating, we have okay, that will simply give us ei. This becomes dy all over the x. So I've integrated the squared y over the x squared. It will not transpose to dy over the x. And this is now equal to, I have 5.7. Now remember, I'm integrating with respect to x. So that means if I integrate x here, I will simply have x squared all over 2. And since this is not a definite integral, it does not have a limit. So which means I'm going to introduce what is called a constant of integration. So I said in the introductory video that always keep the constant outside of what? The Macaulay's brackets. So we are simply going to have plus C1. This C1 is simply what? Constant due to what? The integration. Then you put down your Macaulay's bracket. I also said that if you're integrating the functions or the expression in the Macaulay's bracket, consider it as what? A single variable. The same way I integrated x here, just x, and I have x squared over 2, that is the same way I'm going to integrate x minus 2. I will see it as what? A single variable. So if I integrate x minus 2, I will simply have minus 5 into x minus 2 all squared all over 2. The same way I integrate what? X here to have x squared over 2, that's the same way I'm going to integrate x minus 2 according to Macaulay's method. You consider that as a single function. The same way you integrate a single function. So you simply have x minus 2 all squared all over 2. Okay, so I will put down my bracket again. This is minus 7. Same thing here. I have x minus 4. So I will also integrate it what? As a single function. So it becomes x minus 4 all squared all over 2. So I have this for the first integration. Okay, so I can maybe rewrite this. This becomes ei dy all over the x equal to, so from here, notice that I can simply have 5.7x squared all over 2, okay, plus c1 into, this can also give me minus 5 all over 2 into x minus 2 all squared, okay, minus 7 over 2 into x minus 4 all squared. So I can have this. So let's break these values down now. I have ei dy dx to be equal to simply 5.7 divided by 2, 2.85x squared plus c1 into, of course, 5 divided by 2 simply gives me minus 2.5 into x minus 2 to the power of 2. Okay, put down my bracket. 7 divided by 2 gives me minus 3.5 into x minus 4 all squared. So this is called the slope equation because I have dy dx. Dy dx simply stands for slope. But the question says we should find deflection. So which means we need to now what? Integrate this equation again to obtain the deflection equation. So integrating again, okay. integrating again, we have, okay, this is simply ei. So if I integrate dy dx with respect to x, I will simply have y. So if I integrate the y dx, I will simply have y. Now this is equal to, I put down my 2.85. Okay, of course, I'm integrating with respect to x. So I have here x squared. If I integrate x squared, I will simply have x cubed all over 3. If I integrate x squared, I will simply have x cubed all over 3 plus, I will also integrate the constant c1, and if I integrate constant c1, if you're integrating a constant, always attach the variable of the integral to it. So this simply becomes c1x. But then again, I said you put all the constant outside the Macaulay's bracket. Since I'm taking a second integration, it means I'm going to have a second what? Constant. So you put that constant also plus c2 due to the second what? Integration. Okay, put down your Macaulay's bracket. Now the same thing applies. You also integrate this function as what? A single variable. You're not to expand this bracket, integrate it as a single variable. The same way you integrated here x squared and you had x cubed over 3. That's how you're going to integrate x minus 2 squared. You consider it as a single variable. So we simply have here, we'll put down our minus 2.5. So if we integrate x minus 2 squared, we simply have x minus 2 to the power of 3 all over 3. Same thing applies here. X minus 4 squared will give us x minus 4 to the power of 3 all over 3. Okay, so we'll put down our bracket minus 3.5. Okay, so we'll have here x minus 4 to the power of 3 all over 3. So we'll simply have this. Okay. Okay, so we simply have EIY. So if we rewrite those equations, this is now equal to, so here we have 2.85 divided by 3. That gives us 0.95 x cubed. Okay, we have 0.95 x cubed. So so plus C1x plus C1x plus second constant C2, then open up your Macaulay's bracket. Here we have 2.5 divided by 3. So that's simply minus 0.83, okay, into x minus 2 to the power of 3. Finally, put down your Macaulay's bracket. We have here 3.5 divided by 3. So that's minus 1.17 into x minus 4 to the power of 3. So we have that relationship. So at this point, I said to obtain the values of these constants C1 and C2, we simply take boundary conditions. Now, what are the boundaries? Boundaries are simply what? Between A and the last point of the beam, D. Each point here two are boundaries. B is a boundary, C is a boundary, D is a boundary. But to take a very effective boundary condition, we always have to start from the beginning. So boundary at point A. So consider at A. So at A, okay, at this point, remember we said X runs from point A down to what the point of section. We call that distance X, which means it actually started from point A. Now at point A, which is very at this point, X does not have a value. At point A, the value of x is simply equal to 0 because this is where that's the starting point of the distance. So it doesn't have a value at that point. X at point A becomes 0. Meanwhile, at this same point A, there is no deflection. The beam cannot be deflected at about this point because there's a load acting what? Upwards here to resist deflection. So beam cannot deflect at that point. So therefore, y, which is deflection, is also what? 0. So these are the boundary conditions. Okay, at A, x is 0, y is also 0. So we simply what? Substitute these two values into the equation for what? X and y. Let's try it now and see. Okay, so we now have E, I. In place of y now, we simply said y is 0. So in place of y here, we simply put in the value as 0. And this is now equal to Here we have 0.95x cubed, but x is 0. So we simply have 0.95. Okay, in place of x there, we'll simply put in the value as 0 cubed. Okay, plus c1x. So in place of x here, also put in 0 plus c1 into 0 plus c2. Open up your first Macaulay's bracket. We have here minus 0.83. In place of x here, simply put 0. So that simply gives us minus 0.83. Okay, in place of x, we have 0 minus 2 to the power of 3. Finally, the last bracket, we have minus 1.17. Okay, 1.17. So in place of x there, we have 0 minus 4 to the power of 3. Okay, we have this. Okay. Okay, so here ei times 0 gives us 0 equal to, here we have 0.95 times 0 cubed also gives us 0 plus, here we have c1 times 0 also gives us 0 plus, we have here c2, put it down c2. So put in your Macaulay's bracket. Okay, we have here minus 0.83. This becomes 0 minus 2 remains minus 2 to the power of 3. Put down your Macaulay's bracket. Next is simply minus 1.17 into 0 minus 4 gives us minus 4 all to the power of 3. So according to Macaulay, it says every value in the Macaulay's bracket that is less than 1 should be treated completely as 0. That's Macaulay's method. So every value in the brackets less than 1 should be treated as 0. So I have here minus 2. Minus 2 is of course less than 1. So automatically everything here is simply called 0 according to Macaulay's method. Same thing here. I have minus 4. So since I have negative value inside that bracket, automatically everything here also becomes 0. So those two are off. It means now that I have 0 is equal to, of course, 0 plus 0 remains 0, plus c2 plus 0 plus 0, because here is 0 and the other is 0. So this simply implies that c2 itself is simply equal to 0. So that gives you the value for what? The constant c2. So if you've obtained c2, all you need to do is simply what? Substitute c2 into where? The deflection equation. So substitute the value of C2 into the deflection equation. Since C2 is 0, the deflection equation becomes, okay, the deflection equation becomes okay. So here we have EI, Y is simply the deflection. Okay, here we have 0.9 cube. Here we have 0.95x cube. Okay, plus C1x. Okay, so of course C2 is off because C2 is 0, so it's off. So we put down your Macaulay's bracket, minus 0.83, okay, into x minus 2 all to the power of 3. Put down your Macaulay's bracket, minus 1.17 into x minus 4 to the power of 3. So I have this. So to find the first constant of integration, that is C1, we now apply another boundary condition. This time around, the boundary condition is at point D. So we always take two boundary conditions. The first is at the beginning of the beam, and the second is where at the end of the beam. We'll take the second boundary condition at that point. So at D, the value of x is simply what? Total value. Remember, x runs from point A down to this point of section. So if x extends from point A down to point D, it means x becomes the total length of the beam from point A to D, which is simply what? 2 plus 2 plus 2, and that is 6 meters. So at D, x equals 6. Also, at this point, point D, there is no deflection. At point D, there is no deflection because I have a load acting upwards at that point. So this fluid will resist any form of deflection at that point. So at point D also, y is equal to 0. Y remains 0. But x now becomes total length from A to point D. If that's the case, then we now substitute these boundary conditions into the given equation. We will have EI in place of y remains 0. So times 0 is now equal to, here we have 0.95 in place of x cubed. X now is 6. It becomes 6 cubed, okay, plus we have here C1 times, in place of x, x is 6. So times 6. Okay, so put your Macaulay's bracket, of course, minus 0.83 into x here is 6. So you have 6 minus 2 all to the power of 3. Put down your Macaulay's bracket. Here we have minus 1.17 into x here is 6. So it becomes 6 minus 4 to the power of 3. So I have this, okay? All right, so this gives me, of course, EI times 0 automatically becomes 0. So I simply have here 0 is equal to, here now I have 0.95, okay, multiplying by 6 cubed, 216, okay, plus this becomes 6C1, okay. Put down your Macaulay's brackets. I have minus 0.83 into, here now is 6 minus 2, which is 4. So see that in the Macaulay's bracket now we have positive value, so this cannot be termed as 0. So raised to the power of 3. Okay, put down your Macaulay's bracket. Next thing here, minus 1.17 into 6 minus 4, there is 2 to the power of 3. Again, we have a positive value inside the bracket, so this cannot be termed as 0. All right. All right, so at this point now we have 0. 0 is now equal to, so, all right, so here we have 0.95 multiplies 218, 205.2, okay, plus that will give us 6C1. Okay, so at this point, there's no need to put in the Macaulay bracket anymore because we have positive values inside the bracket, so you can take them off. So we simply have minus 0.83 into 4 cube. 4 cube is 64. Okay, minus, I'm bringing it down, 1.17 into 2 cube is 8. All right, so I have this. So this is now saying 0 equals 205.2, okay, plus 6C1, okay, minus 0.83 times 64. We have 53.12, okay, minus 1.17 times 8, 9.36. All right, so we simply have 0 is now equal to, so we can, of course, collect like terms together. 205.2, we have 205.2. Let's bring all these terms together. Minus 53.12, minus 53.12. Let's also take this here, minus 9.36, minus 9.36, and finally plus 6C1. Okay, so 0 is now equal to, give me 205.2 minus 53.12 minus 9.36. 142.72 plus 6C1. All right, so we have this. So at this point, we need to make C1 subject. All we need to do is simply what, send plus 142.72 over to this side of the equation. Positive sign causes an equal to sign becomes negative. So I'll simply have minus 142.72 is equal to 6C1. Therefore, to make C1 subject, divide both sides by what? 6. So this simply implies that C1 itself is now equal to minus 142.72 all over 6. So this simply implies C1 is equal to 23.7 minus 23. Okay, so C1 is simply equal to minus 23.779. So this becomes value for the first constant. So having known this now, we can now substitute into the deflection equation in place of C1, and then we're going to obtain the deflection equation. Okay. All right. So we can simply say the deflection equation becomes the deflection equation becomes all right. So we have EIY to be equal to, here we have 0.95x cubed, is simply 0.95x cubed, okay, plus C1x, but we know the value of C1 now. C1 is minus 23.79, so that simply becomes minus 23.79x, okay, so we'll put in our Macaulay's bracket, okay, we have here minus 0.83 minus 0.83 into, we have x minus 2 cube, all cube, put down your Macaulay's bracket. Next we have minus 1.17 minus 1.17 into x minus 4 cube, x minus 4 all cube. Okay, so I can take this side off now. All right, so this becomes the deflection equation. This is now the real deflection equation. Now the equation says find the deflection at points B and C. So which means they are asking us to find deflection at point B and also at point C. At point B, what is the value of x? The value of x is simply what? 2 meters. Simply from point A down to point B, x becomes this distance 2 meters. So that gives us deflection at point B. Okay, so at B, x is simply equal to distance from point A. Remember, x runs from point A. So it becomes distance from point A to point B, which is simply what? 2 meters. X equals 2 meters. So deflection at this point, y of course is the deflection equation. So y is simply what? YB. So we simply call that YB. That is deflection at point B. So we substitute these boundary conditions into the given what? Deflection equation. So we simply have EI. So in place of y now, it becomes YB, which means deflection at point B. And this is now equal to 0.95. In place of x now, we have 2. It becomes 2 to the power of 3 because this is 2 cubed minus 23.79, okay, minus 23.79. X here stands for 2, so times 2. Okay, put down your Macaulay's bracket. Now the essence of the Macaulay's bracket is always to investigate, like I said, if every value inside the Macaulay's bracket is less than 1, automatically every value in that bracket becomes 0. So you must always work with the Macaulay's bracket. So we have here minus 0.83 into x is 2. I simply have 2 minus 2 to the power of 3. Open your Macaulay's bracket again. We have minus 1.17. Okay, into here x is 2. So it becomes 2 minus 4 to the power of 3. Okay, so this is simply EI. YB is now equal to, so I have 0.95 multiplied by 2 to the power of 3 is 8. I simply have 8 minus 23.79 times 2. Okay, so this is simply 23.79 times 2. All right, so we have 47.58. So open your Macaulay's bracket. This is minus 0.83 into, of course, 2 minus 2 here automatically is 0 to the power of 3. Open your Macaulay's bracket. We have minus 1.17 into, here 2 minus 4 is simply minus 2 to the power of 3. So observing the Macaulay's bracket, of course, although we have 0 here, 0 multiplies everything here becomes 0. But then again, 0 is less than 1. So if everything in Macaulay's bracket is less than 1, automatically treat it as what? 0. So this is completely 0. Next thing here, I have minus 2. And minus 2 is also what? Less than 1. So we treat everything here as 0 according to Macaulay's theorem. So that means those parts are actually off. This becomes EI YB equal to 0.95 times 8. We have 7.6 minus 47.58. Of course, everything here is off 0. So therefore, 7.6 minus 47.58. So EIYB is now equal to, so we said 7.6 minus 47.58 gives us minus 39.98. Okay, so we have this. So the question says find the deflection at point B, which is simply YB. Therefore, it means we have to divide both sides by flexural rigidity, which is EY. Therefore, deflection at B, which is YB, is simply equal to minus 39.98 all over EI. So this gives you the value to that deflection. Now, it has a negative value simply because always deflection is what? Downwards. That's why you have a negative value. Not like it's always anyways. Of course, there are situations where we'll have positive values to show deflection is simply upwards. But in this case, the deflection curve is downward, so it has a negative value. All right, so that's how to find deflection at point B. Next question says find deflection at point C. So still the same thing. We know the deflection equation. At point C, x equals what? 2 plus 2, which is 4. So we can find deflection at that point. Let's try it and see. All right, so at C, x is equal to total length from A to C, which is simply what? 4. So at C, x equals 4, and y at that point, deflection at that point is simply called deflection at point C. So we simply call that YC. So we simply substitute these boundary conditions into what? The deflection equation. All right, so we have E, I, in place of Y, it becomes YC, which means deflection at point C. And this is now equal to, we have 0.95, okay. In place of x here, we simply put in the value of x as 4. But since x here is cubed, it becomes 4 cubed to the power of 3, okay. Minus, here we have 23.79 into x. X now is 4. Okay, so Macaulay's bracket, we have minus 0.83 x minus 2 cube, which is minus 0.83 x. In place of x now, x is simply 4. So it becomes 4 minus 2 to the power of 3. Okay, put down your Macaulay's bracket, which is the final one. We'll have here minus 1.17 into x here is 4, becomes 4 minus 4 to the power of 3. All right, so you have that. So let's evaluate now and see. Okay, so we have EI YC equals, so this is 0.95, 4 cube is 64, okay, minus 23.74 times 4, so we have 95.16 minus, okay, put your Macaulay's bracket, minus 0.83 into, here I have 4 minus 2, which is actually 2 and is positive, okay. Open your Macaulay's bracket, here I have minus 1.17 into 4 minus 4, automatically this is 0 to the power of 3, so I have that, okay. So EI YC is now equal to, so 0.95 times 64, okay, we have 60.8 minus 95.16, okay. Here now, of course, I have what's the Macaulay's bracket to be positive, so I can take off this Macaulay's bracket. So this gives me minus 0.83 into 2 to the power of 3 gives me 8. Okay, here I have 0, of course. This multiplies 0 automatically. Everything here becomes 0. So this is off 0. Okay, so EIYC is now equal to, so I have 60.8 minus 95.16. Okay, 60.8 minus 95.16 minus 34.36 minus 0.83 multiplies by 8 minus 6.64. So I have this. Okay, so at this point, this simply implies EIYC is now equal to minus 34.36 minus 6.64. All right, so we have minus 41. Okay, minus 41. So we simply make YC subject by dividing both sides by what? Flexural rigidity, EI. So that simply implies deflection at point C is simply what? Minus 41 all over EI. So this gives us the answer to that deflection. All right, guys. I hope you find that video very educative and helpful. Please, if you do, don't forget to share your thoughts in the comment section. I will see you in the next video with more problems on deflection of beams by Macaulay's method. All right, guys. Thanks and cheers.